In this video, we're going to find the area of the region bounded by the parabola y equal x squared plus 2, the line y equal minus x, vertical line x equal to 0, and x equal to 1. So if you look at y equal x squared, that parabola has vertex at the origin and opens up because the coefficient is positive. You add a 2, it just moves it up. So that's the graph of the parabola. Vertex at 0, 2. Opening up, the line y equal minus x passes through the origin. Positive line would go up. Negative slope there of -1 brings it down this way. That's what the graph looks like. Of course, x equal to 0. That's your y-axis. And then we have the line x equal 1. So the region we're talking about is right in here, contained between those lines. Right in there. And you can use horizontal or vertical triangles, whatever's convenient. Now in this particular case, if I draw a rectangle, say this way, coming down, vertical rectangle. Again, for the area here, in these types of problems, we're using the fact that the area of a rectangle is length times the width. So the length would be this distance here from the line to the parabola. So to find the length of that is just the top curve minus the bottom curve. Using horizontal ones, it's the right minus the left. So if it's a vertical rectangle you're using, the width would be dx, so you're integrating with respect to x. And then we just need the height. So the integration for the area of this region goes from this point here, the origin, first value is 0 then, lower limit, to the vertical line x equal to 1, y-axis x equals 0, below the graph, parabola, and above the line. So it goes from 0 to 1. So the integration would be from 0 to 1 here. And then the length of the rectangle, again, based on the graphs, would be the parabola, top curve minus the bottom curve, will give you the length. So it'd be x squared plus 2 minus the bottom curve, which is minus x here. So remember, when we do the area using the definite integral, we're really taking an infinite number of little rectangles, and we go from 0 to 1, we're adding all those pieces, so all the areas of each rectangle. And then of course the dx represents the width, the general width of each of those. We can continue over here then. This is going to equal then the integral from 0 to 1, and then it'll be minus a minus x here, so this will be x squared plus the x. I put the x over here, and of course I got the plus 2, and then it's dx. And then the value of this integral then, based on the area, the definite integral, and area, would give you the area of this particular region. So all you have to do now is just integrate, basic integration, term by term. X squared, add 1 to the exponent, we get 3 there, divide by 3, plus for the x, add 1 to the exponent, we get a 2, divide by 2. Integral of 2 with respect to x is 2x. And we just integrate from 0 to 1. We evaluate the polynomial expression at 1. So 1 to the third is 1. 1 to the second is 1. 1 times 2 is 2. So I get a 1/3 here, 1/2 here, plus 2. And then it's minus the value of this expression at 0. So we put a 0 wherever the x is. So I got 0 to the third is 0, over 3 is 0. 0 to the second is 0, over 2 is 0. 0 times 2 is 0. So all of that is just 0. Combine these, the common denominator here is going to be 6. So 3 into 6 is 2 times 1 is 2. 2 into 6 is 3 times 1 is 3. And put this over 1. 1 into 6 is 6 times 2 is 12. 2 and 3 is 5, and 12 is 17 over 6. So the area of that region is 17 over 6. And because we're dealing with area, it doesn't give the units here, so we can just say square units. So here's your setup here for the integral. Again, top curve minus the bottom curve gives me the length of the representative rectangle that we're using, in this case a vertical rectangle. And then the dx represents the representative width, which of course, when we sum these up over the interval from 0 to 1, we get the total area. Thanks for watching. We'll see you next time.